Lesson: Theoretical models and techniques. Theoretical models and techniques play a pivotal role in the realm of AI-driven cyber threat intelligence, shaping the methodologies and tools used to detect, analyze, and mitigate cyber threats. These models and techniques form the backbone of cybersecurity strategies, enhancing the ability to predict and respond to potential threats with greater accuracy and speed. This lesson delves into the core theoretical models and techniques that underpin AI applications in cyber threat intelligence, showcasing their importance and effectiveness through detailed examples and statistics. At the heart of AI-driven cyber threat intelligence are machine learning models, which can be broadly categorized into supervised, unsupervised, and reinforcement learning. Supervised learning involves training algorithms on labeled datasets where the desired output is known. This approach is particularly effective in detecting known threats through pattern recognition. For instance, decision trees, a type of supervised learning model, can classify incoming network traffic as benign or malicious based on historical data. The accuracy of these models can be quite high. For example, decision trees have been shown to achieve an accuracy rate of up to 98% in malware detection tasks. Unsupervised learning, on the other hand, does not rely on labeled data. Instead, it identifies anomalies and patterns that deviate from the norm, which is crucial for detecting novel or zero-day threats. Clustering algorithms, such as k-means, group similar data points together, allowing for the identification of outliers that may indicate a cyber threat. One study demonstrated that k-means clustering could detect 95% of previously unknown malware samples by identifying patterns in their behavior. Reinforcement learning, a third category, involves training an agent to make decisions by rewarding desirable actions and penalizing undesirable ones. This technique is highly effective in dynamic and complex environments, such as network defense, where the threat landscape is continually evolving. A notable application of reinforcement learning in cybersecurity is the development of automated intrusion detection systems that adapt to new threats by learning from past experiences. Deep learning, a subset of machine learning, has also made significant strides in cyber threat intelligence. Neural networks, particularly convolutional neural networks and recurrent neural networks, have garnered attention for their ability to process and analyze vast amounts of data with high accuracy. CNNs, with their hierarchical structure, excel in image recognition tasks, making them suitable for identifying visual patterns in malware signatures. RNNs, which are adept at handling sequential data, have been effectively used in analyzing network traffic over time to detect anomalies indicative of cyber threats. A study on using CNNs for malware detection reported an impressive accuracy rate of 99.6%. In addition to machine learning and deep learning models, natural language processing techniques are instrumental in cyber threat intelligence, particularly in analyzing unstructured data from various sources, such as social media, forums, and darknet sites. NLP algorithms can extract valuable insights from textual data, such as identifying emerging threats, understanding hacker motives, and tracking the spread of malware. Named entity recognition, an NLP technique, can identify and classify entities within text, such as IP addresses, domain names, and malware names. For example, by analyzing cybersecurity forums using NER, researchers can detect early warnings of potential cyber attacks and take proactive measures. Graph theory also plays a crucial role in AI-driven cyber threat intelligence. Cyber threat intelligence often involves understanding the relationships between different entities, such as IP addresses, domains, and malware samples. Graph-based models, such as knowledge graphs, can represent these relationships and facilitate the identification of interconnected threats. For instance, a knowledge graph that maps the relationships between different malware families can help analysts understand the evolution of malware and predict future variants. In a study on using graph theory for cyber threat intelligence, researchers demonstrated that knowledge graphs could reduce the time required to analyze threats by 30%. Another critical technique in AI-driven cyber threat intelligence is anomaly detection, which aims to identify deviations from normal behavior that may indicate a cyber threat. Anomaly detection algorithms, such as isolation forests and autoencoders, are particularly effective in identifying previously unknown threats. Isolation forests, for example, isolate anomalies by recursively partitioning data, making them well-suited for detecting outliers in network traffic. Autoencoders, a type of neural network, learn an efficient representation of data and can identify anomalies by measuring reconstruction errors. A study on using autoencoders for anomaly detection in network traffic reported a detection rate of 97%. To further enhance the effectiveness of AI-driven cyber threat intelligence, it is essential to incorporate threat intelligence sharing and collaboration. By sharing threat intelligence data across organizations and sectors, the collective defense against cyber threats can be strengthened. Platforms such as the MITRE ATT&CK framework provide a comprehensive knowledge base of adversary tactics and techniques, enabling organizations to understand and defend against cyber threats more effectively. The use of standardized formats, such as STIX and TAXII, facilitates the sharing of threat intelligence data in a structured and automated manner. Despite the advancements in AI-driven cyber threat intelligence, challenges remain. One of the primary challenges is the adversarial nature of cyber threats, where attackers continually evolve their tactics to evade detection. Adversarial machine learning, a field that studies how attackers can manipulate AI models, highlights the need for robust and resilient AI systems. For instance, attackers can generate adversarial examples that are designed to fool machine learning models into misclassifying malicious activities as benign. To address this challenge, researchers are developing techniques such as adversarial training, where models are trained on both normal and adversarial examples to improve their robustness. Another challenge is the interpretability of AI models. While complex models, such as deep neural networks, achieve high accuracy, they often operate as black boxes, making it difficult to understand their decision-making processes. Interpretability is crucial in cybersecurity, where analysts need to trust and understand the rationale behind AI-driven decisions. Techniques such as LIME and SHAP are being developed to provide insights into the decision-making processes of AI models. In conclusion, theoretical models and techniques are fundamental to the development and application of AI-driven cyber threat intelligence. Supervised, unsupervised, and reinforcement learning models, along with deep learning, natural language processing, graph theory, and anomaly detection techniques, provide the foundation for detecting, analyzing, and mitigating cyber threats. The integration of threat intelligence sharing and collaboration further enhances the collective defense against cyber threats. Despite the challenges posed by the adversarial nature of cyber threats and the interpretability of AI models, ongoing research and advancements continue to improve the effectiveness and robustness of AI-driven cyber threat intelligence. By leveraging these theoretical models and techniques, organizations can better protect their digital assets and infrastructure from evolving cyber threats.